Welcome to Notes on Torque. Okay, so a few things about torque before we kind of get into the mathematical things. Okay, so torque on an object causes rotation if it's an unbalanced torque. Okay, causes rotation. There we go. Okay. So an unbalanced torque can cause rotation. Okay. Torques can also only occur on objects with a definite shape. So what do I mean by a definite shape? I mean like a bar or a sphere or a disc, something like that. But what I'm especially thinking not being able to cause a torque is a point mass. Okay, is a point mass. Okay, so torques are caused by forces at distances from the axis of rotation of an object. Okay. And this distance from the axis of rotation is often called the lever arm. Okay, so we need a force applied at a distance from the axis of rotation. And the axis of rotation for most objects, unless there's a pivot point, is going to be the center of mass, which is also the center of gravity. Okay, which is where the force of gravity acts. Okay. So in addition to being forces at a distance, the force needs to be perpendicular to the lever arm. Now, the whole force doesn't need to be perpendicular to the lever arm, but a component of the force needs to be perpendicular to the lever arm. So let's talk about the equation that defines this idea of torque. We're not going to talk about the rotation part yet, okay, the causing of rotation. We're really just going to talk about the forces at a distance part and those forces needing to be perpendicular. This causes rotation part we'll get into in later videos where we talk about equilibrium and Newton's second law for rotation. Okay, so torque, like I said, is defined as a force applied at a distance from the axis of rotation, and that force and lever arm need to be perpendicular. So this F here is the force. Okay, R, even though we're used to it meaning radius, it doesn't mean that. It means distance from axis of rotation. Okay, and this sine theta here takes into account the perpendicular component. Okay. So our most common kind of torque problem would be, let's say we have a bar, okay, and the end of the bar is pivoted there. Okay, so that's what that dot is. It's a pivot. Okay, and I apply a force like this. Okay, so that force is at a distance from my axis of rotation, R, and luckily it's already perpendicular to that lever arm. So I could say that the torque applied by that force F is just going to be FR. Okay. Now, one thing students often forget is they'll just say, oh, well, the torque from F is just F. They'll forget that R component. That is very, very wrong. You have to take into account R. That's part of the definition of a torque. Okay. And the units for torque is going to be a Newton times a meter. Okay. So another example that we might have is we might have our same kind of door, but we might have a force applied at an angle theta. Okay, again, at a distance r. Okay, so for this force that is applied, right, at that distance, the only part of the force that's going to actually produce a torque is the perpendicular component, which I'm drawing here in red. Okay. Now, if I was to draw in the parallel component, okay, which would be this gray force here, okay, we see that that forms a right triangle. Okay. And if this is theta down here, then this angle up here is theta, okay, which makes my perpendicular side opposite of the angle, which is why I use sine. Okay. So in this case, my torque from force F wouldn't just be Fr. We would need to take into account that perpendicular part, which we do by multiplying by sine of theta. Okay. Now, there are instances where we don't always use sine, okay? So when you see this on your reference table, I don't want you to think that it always has to be the sine. I want you to remember that that needs to be the perpendicular component, which sometimes, depending on the angle we're given, might mean cosine. So an example of that would be our typical ladder problem. So we have a ladder up against a wall, and let's say there's a person standing on the ladder, and we want to find the torque from the person. Okay. Well, the person is going to exert a downward force on the ladder, and because the person is at rest, the downward force acting on the ladder is going to be equal to the weight of the person. All right, so that's our force part, is just the FG of the person. Now we need the distance from the axis of rotation. Now, on this, we don't really know where the axis of rotation is, so we can pick it. So I'm going to choose this bottom location here as my axis of rotation. Okay, so my lever arm goes like this. It's the blue line. Okay, now let's say that whole lever arm is the length of the ladder, has a distance L. And let's say that the person is making our lives easy and they are at L over 2. Okay, so that would be my R value, would be L over 2. Okay, now the person's force of gravity on the ladder is not perpendicular to the ladder. Okay, unfortunately for us. So what we need to do is we need to figure out the component perpendicular to the ladder. So that component is going to be looking something like this. Okay, but I'm going to erase that for now so I can show you how we're going to get the angle. Okay, so we can't exactly say that the angle that the FG makes with the ladder is theta because it's not. But what we can do is we can kind of pretend to drop this down and make a triangle. Now, if this is 90 down here, that means this angle in here has to be 90 minus theta. Okay? So what that means for that perpendicular component, which again was right here, okay, and again my parallel component would be something like that. So that means this angle in here is 90 minus theta. And again, we're seeing I can use sine. Okay? So I would use sine of 90 minus theta. But here's the thing that the AP exam loves to do. This is sort of ugly. It's not really, it's not really simplified. So what the AP exam will ask you to do is they will ask you to remember that the sine of 90 minus theta is equal to the cosine of theta. So an example of that would be like the sine of 60 is equal to the cosine of 30. So if this were a multiple choice, this question would probably look like not FG L over 2 sine of 90 minus theta. It would look like FG from the person L over 2 cosine of theta, just to simplify it, okay? But that's really the only time where we see this kind of flip to cosine, is where we have situations like this. Okay. The other thing to remember with torque is, of course, that we don't always have just one torque. Okay, so let's go back to our bar example. We might have a force F getting applied here. We might have a force F over 3 getting applied there. Okay, so let's say that this whole length is a distance r, and this F down here is at, well, it looks about like 2/3 r. Okay, so if I wanted to find what's considered the net torque, which I can also write as the sum of all the torques, I would need to add together the torque from F and the torque from F over 3. But here's the thing. Those two forces are not going to create torques in the same direction. So what we need to make sure of is that we're taking into account direction. Okay? So when we get into problems involving equilibrium and Newton's second law, we usually say direction of motion is positive. Okay? But in a situation like this, we're going to say that counterclockwise, or CCW, is positive and clockwise is negative. So what I mean by that is, if that force would cause the bar to move counterclockwise, we would consider it positive. If it would move clockwise, we would consider it to be negative. Okay, so how do we figure out clockwise versus counterclockwise? Well, first we identify our axis of rotation. Okay, and I'm going to redraw these forces so they're actually like a free body diagram, meaning they start on the object and move outwards. Okay, so this force was down like this, and then we had an F over 3 like that. Okay, so that F over 3 was at 2/3 r, and this F was at r. Okay, so in order to figure out positive versus negative, what you're going to do is you're going to follow the force, okay? And this is something you should not draw on official free body diagrams. You should draw this off to the side, okay? But you're going to follow the force and then curve towards the axis of rotation. And that's going to give you the direction of rotation. So this direction of rotation is clockwise. So that torque is considered negative. Whereas this direction of rotation is considered counterclockwise. So that's going to be positive. Okay. So when I'm taking into account my torques, the torque from force F is actually going to be a negative FR, and my torque from F over 3 is going to be positive, and then 2/3 R. Okay, remember, force times distance. So let me rewrite this. F over 3, 2/3 R minus FR. Now, when it comes to combining something like this, what we want to do is we want to combine all of the coefficients, or all of the numbers, first. So we want to combine 2/3 and 1/3, and they're being multiplied. So they're going to multiply together to give us 2/9. So we're going to pull that number out front. And then F times R. Okay? Then minus FR. Okay? So now we have to subtract fractions. These are like terms since the variables in it are exactly the same. So we're going to subtract 1 FR from 2/9 FR. But I need common denominators, so I'm actually going to make this 9/9 FR, which gives me, so 2 minus 9 is -7. And I don't change the denominator when I'm doing addition or subtraction. So I have -7/9 FR, and that's considered my net torque acting on this bar. Okay. The last thing I want to talk about in this video is torques on objects rolling across surfaces. Okay. So let's say we have a sphere, and it is rolling to the right. Okay. And like that. Okay. So acting on the sphere are going to be similar forces that would act on a box rolling or sliding across the surface. We have a force of gravity, we have a normal force, and we have a force of friction. But we have to make sure that we're placing those forces where they are acting. So the force of gravity acts at the center of mass, which I'm going to abbreviate as COM. The normal force is an interaction force between the surface and the sphere, so that has to start at the surface. Okay. Same with friction. Friction is an interaction between the surface and the sphere, so the force of friction has to act at the surface. Okay. So gravity is going to point straight down. The normal force doesn't need to be that big. Normal force is going to point straight up, and friction is going to point to the left. And I'll talk about why friction points to the left in a second. So now let's think about which of these are providing torques. Okay. Well, remember, the definition of a torque is a force at a distance from the axis of rotation perpendicular to the lever arm. So the axis of rotation for the sphere is going to be the center of the sphere, which means Fg does not produce a torque. Okay. The normal force, though, is a distance from the axis of rotation. But the thing is even though our axis of rotation is that center part there, our lever arm is this blue dashed line. It's the line connecting the center, the axis of rotation, and where the force is acting. The normal force is actually parallel to that line, which means that the normal force cannot create a torque. So again, gravity had no torque because there was no R. Normal force has no torque because it is parallel to R. Okay. So that leaves friction. So friction is acting at a distance, and friction is perpendicular to that lever arm. So friction does produce a torque. Okay. Now the reason why I knew that friction had to point to the left is because if my object is rotating clockwise as shown, the only way for friction to create that clockwise rotation is if it's pointing to the left. Again, remember, we can follow our force and then curve towards the axis of rotation to help us figure that out. Okay, so friction is actually what's causing this object to roll. And that is the case in any rolling object. Okay, you need friction because friction produces the torque, which causes something to roll. Otherwise, if friction's not there, this sphere would just slide across the surface. Okay, because there would be no force acting at a distance and perpendicular. And that is it for the basics of torque.